Hi, everyone. Welcome to our first webinar this year. We've decided to kick off the webinar series this year with a very important and I would say a must technical requirement for NetConf-based network elements, which is the proper support of transactions. Something that can either make it for a device to be fully automatable or can break automation and actually nullify the benefits of NetConf. So I'm going to be recording this meeting, obviously. I will also like to save a couple of maybe 5 or 10 minutes at the end of this presentation for questions. But if you have any question during the presentation, please use Q&A section. You can see that on the right side at the bottom part. You can open that, ask your questions. We might be able to answer those questions as we see them come. Otherwise, we'll save them till the end. With that, I'd like to ask my colleague, Michal, to take it over from here.
Okay, thank you, Nabil. So hello, everyone. First, I'll start sharing my presentation. So let me share it. And I hope that now you just move this out. You should be able to see my first slide.
Yes.
Is it correct? Okay.
Yeah, thank you.
So we can start now. So hello, everyone. Welcome to this workshop related to transactionality and also to Cisco products, NSO and ConfD. My name is Michal Novák and I'm part of Cisco ConfD SA team. During presentation, as Nabil said, you can ask questions in Q&A panel and my colleagues will try to answer them. So let's take a look at the content of the presentation. First, we'll look at basic transactionality principles and differences between devices. We show how devices connected to Cisco NSO, which stands for Network Service Orchestrator, participate in the network-wide transaction. Next, we explain how devices can be connected to the NSO with use of NSO-Net, Network Element Driver. And we mention advantage of standard network management protocol like NetConf. We discuss how non-transactional devices can be adapted to be transactional and what are the options to make them transactional. We summarize common transactionality issues that should be considered from point of view of northbound interface, adaptation layer, and device itself. After that, we'll show how non-transactional device can be converted into transactional with help of Cisco ConfD, configuration management agent. What are the common tasks? We will discuss how ConfD CDB subscriptions can help us with this task. We show simple ConfD example application doing such adaptation, and you will see the example in action in short demo. At the end, we summarize what we have seen and provide references to the resources. So I believe we can start now. Basic transactionality concepts, they are most probably well known to you, so we can just briefly summarize them. We know that all operations in transaction are treated in an atomic way. This means all operations complete successfully, and if not, nothing would be changed to the system the transaction was running on. During failure, system is restored to its original state. Transactionality is important to implement rollback support, and many times rollback implementation is much simpler when transactionality is supported. With transactionality, the automation and programmability is also possible. Transaction can be seen as independent unit of work with ACID properties, and these properties are atomicity. It means all operations within transaction are treated as single unit. Consistency. Data is in consistent state. That means all data model constraints are fulfilled before transaction starts and after transaction is finished. Data are in consistent state. And isolation. This means that concurrent transactions may be running and they do not influence each other. And last property is durability, which says that if transaction was done, it was done permanently and it wouldn't change even if after the transaction system fails. This requires that transaction is recorded in some permanent memory. Now let's take a look at transactionality from point of view of devices. Device can be transactional, and such device supports transactions. It usually implements transaction management protocol, for example, NETCONF with commit capabilities. These devices can be easily integrated with network orchestrators without special adaptation. Transactional devices are well suited for programmability and automation, and they usually support rollback, or rollback is simpler to implement. And there are devices that are not transactional. Transactions are not supported. For example, SNMP devices, devices with proprietary CLI. And this means that one operation within transaction can bring device into failed state or into in-between state. Usually special knowledge is needed to configure such devices. Configuration commands must be sent in a specific order. Commands must follow rules, otherwise they may fail. Very often skilled human operator is required with the knowledge of the device. This means that automation is difficult and such devices are very often expensive to operate from configuration point of view. They also do not provide simple rollback support. But we can also say that such devices may be cheaper to develop and they may evolve from some successful proof of concept. Very often they operate fine and may be performant, but they are not reliable from configuration point of view. There are also a wide range of legacy systems that do not support transactionality. And because of this, it makes sense to consider adding transactionality layer to non-transactional devices, which we will discuss later on. Let's explain term network-wide transaction used in network orchestrators like Cisco NSO, which stands for Network Service Orchestrator. NSO can manage configuration and states of several devices at the same time. And such devices can be of different types and vendors. Configuration is thus spread over all devices and can be seen as large configuration of the whole system or network. We can call it network-wide configuration. From configuration point of view, NSO is fully transactional and transactionality is preserved over all devices. Transaction over network-wide configuration can be called network-wide transaction. This requires all connected devices must ensure some level of transactionality, either native or added by some wrapper. NetConf devices with NetConf protocol have great advantage in NSO as they are supported out of the box. But even NetConf devices can have different level of transactionality. For example, some may support confirm commit capabilities, some may not. NSO tries to handle this in most optimal way. For example, issue abort commit when confirm commit is present versus rollback if only commit is available. In this way, network-wide transaction is less error prone and may be more performant. So Once we know how the devices are connected to NSO, we can talk about nets. Net is network element driver, and it can be seen as adaptation to make device NSO friendly. So it can be connected or plugged to NSO. Net interface supports transactionality. For example, functions like prepare, abort, commit, revert, persist that are called by NSO. With net, device is normalized as young data model transactional device. Depending on the device type and device transactionality support, different nets must be used. Some of them are available out of the box with NSO. The other requires development with programming skills. So now let's take a look at three most commonly used nets. First one is NetConfNet, which requires NetConf capable device, ideally with commit capabilities. NSO knows how to work with NetConf devices. To create net, we only need device data model as YANG files, and then use NSO command to build net package. We can also use NSO net builder, which can download data models directly from device via NetConf if device supports this. In some cases, NetConf devices may support only startup running capabilities, so they are not fully transactional. But even such NetConf devices can be plugged to the NSO as well, as Net knows how to add transactionality layer itself. Another net type is CLI net. A net that is built around existing CLI of the device. CLI net is not easy to implement. It depends on the transactionality support of the original CLI. It also depends on standard behavior and side effects of the CLI commands. NSO provides a helper interface, CLI net, called CLI net, to simplify development of CLI nets. Last net that we discuss is generic net. It's usually most difficult to implement. Well, it again depends on the device, and it requires implementing full net interface programmatically, which is expensive. Once we have a net for the device, we can connect it to NSO. We can mix devices with different nets as shown in the picture. Net itself can be seen as transactionality adaptation layer over device, even over non-transactional devices, but there are also some disadvantages. And that means that net is not part of device. So when device is updated, one makes to make sure that net still works or update net. And also net runs inside NSO, which may not be desirable if net is complex. So it's better to have net as simple as possible. And for this, it's necessary that transactionality is supported by device itself. So as we have learned, transactional devices have advantage. And for this reason, it's worth to adapt non-transactional device by adding transactionality layer, especially when device performs well. For example, some routers, switches, and so on. And this enables automation and programmability and simplifies to use such devices in network with other devices in network orchestrators. There may be different approaches to implement transactional adaptation layer. One approach is to create proprietary application. This application can communicate with the device, or it can be even wired into device source code. Such implementation can be costly and it can introduce new errors. Other approach is to use existing management agent with APIs that simplifies implementation of the transactional layer. Example of such management agent is Cisco ConfD with its programmable APIs. The adaptation itself can be non-standard. That means it provides some non-standard transactional protocol This protocol can be simple and easy to implement. On the other hand, network automation layer in orchestrator has to learn it and make its own adaptation to it. Device cannot be easily plugged. This disadvantage disappears when standard management protocol like NetConf is implemented within adaptation layer. This is another reason to choose existing management agent for device adaptation, as it usually supports standard protocols. Suggested approach is to look for management system with NetConf support. Now let's discuss transactionality issues. Transactionality issues should be considered from several points of view. One point is northbound interface, example, interface used by network orchestrator. Non-transactionality can cause out-of-sync problem if representation is different from what we have sent via northbound interface, or issue in transactionality can cause this. Then from point of view of adaptation layer, when you add configuration, adaptation layer should hide side effects and dependency on states, for example. Then from point of device, hardware itself, network element, and also from point of YANG data model, which should consider to export only stable parts that do not break transactionality. So these issues must be considered when connecting device to orchestrator or when creating transactionality adaptation layer. It's important to consider them already when YANG data models for the device are designed to hide problematic configuration in exported data models. This slide shows common transactionality issues we very often have to deal with. First transactionality issue is that transaction fails due to dependency between elements in single transaction. For example, you can configure both A element and B in the same transaction. You must configure elements in certain order. This is very often. And this ordering or sequencing issue, which is common in non-transactional devices, needs to be considered. And specific behavior of the device cannot only rely on the contract, which is set by YANG data models. And this must be handled, if possible, by adaptation layer itself. For example, in case of ConfD, ConfD CDB subscription notifications with priorities may split the configuration sent to the device into pieces with correct order. So from northbound interface, the configuration is seen as single transaction, and but this configuration is split by adaptation layer, and device itself is seen as fully transactional. Another issue is that transaction fails and some configuration was modified on the device anyway. This breaks or violates atomicity property in this case, and when a transaction fails, all configuration changes within the transaction should be reverted. ConfD takes care of this as long as the device that participates in the transaction during the validate or prepare phase can handle this properly. This means device shouldn't apply configuration while it's still being validated or even after the validation phase in the prepare phase without implementing proper abort callback. And adaptation layer may try to revert applied configuration, especially when two-phase subscriptions are used, but this is not always possible. So in case device configuration fails after point of non-return, In case of ConfD, transaction is fully committed, and it should be considered as exceptional situation. And in this case, we can or we should issue alarm to operator. But this is exceptional case, as validation should handle this before. Another issue is that transaction fails due to certain previously configured elements were not included in the particular transaction. The resulting configuration should be validated, not only what has been changed in a transaction. This means the whole configuration should be considered and not only what is part of the transaction, as transactions can target small subset of the overall configuration. Adaptation layer can do such validation for non-transactional devices, and what should be validated depends on the device behavior. Transaction fails due to the dependency on prior configuration. For example, element A isn't mandatory, but once created, you can delete it. Such implementation breaks consistency in regards to valid configuration. A manager can go back to once valid configuration. We can assume, for example, that configuration represented by C minus A that is valid is applied. And once we add 8, it becomes just C, which is also valid. But normal management application or automation tool can go back to C minus A because the network element rejects this change. This breaks automation and transactionality. And what is validated in this case is not data itself, but the operation of adding A. This is no longer data model-driven management, as validation in data model-driven management focuses on the resulting data after transaction is committed. There is no easy workaround to this issue. Transaction fails due to dependency on operational state or hardware. For example, you can configure A while the operational state of component is down or hardware is missing. This is example of case when configuration is made dependent on state. In this case, the hardware or state presence affects whether configuration transaction succeeds or fail. This affects automation and makes it less deterministic. Dependency can be directly in the Yang data model. For example, XPath that refers to operational data, not configurational, or it can be present on the device, not visible to northbound interface. It can be sometimes fixed in adaptation layer, for example, temporarily changing state of the device. But one has to make sure that device allow this without misbehavior. Transaction succeeded, but the configuration is different. We sometimes call this out of config. Transaction is only started if the northbound user made changes to the configuration. In some systems, transactions may be handled differently. This problem is combination of two subproblems. One is side effects. System itself adds more configuration. For example, it generates some UIDs and which is something that northbound interface or automation layer didn't say to send to configuration. And this new configuration appears. Another problem is out-of-band configuration, which can be added from some other source, for example, in CLI or by inserting some hardware. The problem mainly occurs if this added configuration is a part of Yang data model contract. But it can also make problem if present only on the device, since adaptation layer has to take this into consideration and set or unset these elements as required by the device. Another issue is that there was no transaction at all, but the configuration changed spontaneously. This is system-driven configuration and not normal manager-driven configuration. This, of course, can be fine if the change isn't exposed to the northbound, but otherwise this is clear out of sync scenario, and configuration validation in transactions should not depend on other state or changes or hardware presence. Spontaneous change can be done by device itself or by some other application not known to the system that started transaction. So let's take a look at ConfD-based device adaptation. ConfD is configuration management agent, which can be used for device adaptation to make device transactional. ConfD has several APIs that support and simplify adaptation of non-transactional devices. ConfD can be part of the device. It can run directly on the device. And adaptation is done in form of ConfD application that connects to ConfD. It's usually socket communication. Once the device is adapted, ConfD automatically provides NetConf support with commit or even confirm commit capability. And such devices can be used with NSO with auto-generated NetConf net, and they support programmability and automation. Adding transactionality to the device with the help of ConfD usually consists of following tasks. You need to identify transactionality issues and rules for the device. Then create device-related YANG data models. Implement validation. Validation ensures data model consistency. Validation can be implemented directly in the YANG file. For example, with YANG constructs like refref, must, when statement, and so on, or as validation point callbacks in ConfD application. YANG file validation is done with XPath expression and is recommended over validation points. On the other hand, it should not be very complex, as evaluation of complex XPath expressions may have impact on overall transaction performance. Callbacks must be programmed, which is more expensive, but are more flexible and can be tailored to each case. Another task is implementation of CDB subscriptions. CDB subscriptions with priorities allow monitoring of selected parts of the data model for changes and get notifications in the correct order. We will discuss subscriptions in the next slides in more details. And sometimes there may be other tasks to a transactionality layer, like data provider callbacks, transformations, and so on. ConfD CDB subscriptions, it's a powerful mechanism for transactionality adaptation. ConfD notifies ConfD application about changes in the configuration, and notifications can be grouped according to the priorities, which is key feature for transactionality layer. Device transactionality issues and rules must be considered, and they almost always contain a required order in which commands must be sent to the device. This order can be reflected by subscription priorities. Notifications about changes are processed and translated to the device-specific commands according to the required device transactionality rules. So let's see subscription context. ConfD application subscribes to parts of the YANG data model. And whenever there is a change in the configuration, ConfD sends data model subscription notifications according to the requested priorities. You can subscribe to one path more than once, This allows to monitor different operations with different priorities. For example, delete operation may be monitored with higher priority. This means before create operation. There may be several subscribers, even across more than one application. This reduces complexity of the application as it doesn't have to handle caching and sorting of the notification messages. In the picture, you can see context diagram. Yeah. Okay. So now we can discuss example application that comes with ConfD. The example application represents transactionality layer and works with hypothetical device with interfaces and VRFs. The device can be configured with text commands, and ConfD example application provides transactionality interface to the outside world. It's implemented with validation, YANG constructs, in our case refref, and with CDB subscription. Several subscription points with priorities are used, and it overcomes the device limitations by sending commands to the device in the correct order. Example also adds full NetConf support to the device. In example, device are printed to the standard output as plain text. So you can see what application does. Identified transactionality rules for the device are following. IP address can be assigned only to existing and configured interface. This means you cannot add IP address in the same step when interface is created and configured. Only interfaces without IP address can be deleted. You must remove IP address from interface first. Only existing VRF can be assigned to the interface. VRF can be deleted only if not assigned to the interface. You must delete VRF from all interfaces first. We have identified dependency and order issues, and such restrictions do not exist in transactional world in ConfD transactional environment, which example adds. The border between this transactional environment and the hypothetical device is ConfD application, which is responsible that the commands are sent to the device in the correct order and according to the rules. To enforce dependency rules, we use YANG data model validation, in our case, refref. To enforce all the rules, we use CDB subscription. So we specify subscription priorities in a way the notifications for the data model paths and operations like delete, create, modify come in required order. First, we get notification for VRF creation as it's not dependent on the other parts, and it ensures rule number 3, VRF must exist before it can be assigned to the interface. Next, we process deletion of IP address under interfaces. This ensures rule number 2, interface can be added only if all IP addresses are removed. After that, we process creation, deletion, or modification of interfaces. In case of delete, we can be sure there are no IP addresses. In case of VRF assignment, we know VRF has been already created. This ensures rule number 2 and 3. Next, creation and modification of IP address is handled. In case of addition, we know interface is already configured. And finally, we handle delete of VRF. At this point, we know that VRF reference was removed from interface in previous notifications, and rule number 4 is satisfied. So let's take a look at example demo. You can find the example in this directory, which is part of ConfD installation. Example details can be found in the example README file and example source code files. The file describes how to build, run, and how to use the example. So now it's time to see the demo in action. So let me switch to my terminal. I hope you can see it now. And we may first display a README file, which has a description of the example, and also it describes how to build it and run it, and how to trigger initial configuration, how to use CLI. So let's build the example and start it. So example has been started, and we can enter also CLI, ConfD CLI, and we can see initial configuration inside CDB. So this is our initial configuration. We have list of interfaces with IP addresses, and there is also a list of VRFs, but in our case, we don't have any VRF configured. At this time, this configuration has not been yet sent to the device, as initial configuration is not triggered by subscriptions, but we can do this by calling trigger operation that sends initial configuration as subscription notification. For this, we use target make trigger. And here are the text commands for our device, for our hypothetical device, that used initial configuration and sorted everything in a way that commands can be accepted by the device without problems. You can see that first interfaces were created and configured, and after that, IP addresses were assigned to the interfaces and configured. So this is according to our rules in our configuration. In ConfD, we can see that IP address is directly assigned under interface, but when commands are sent to the device, first interface configuration is done, and then configuration of the IP addresses. So the order is correctly sorted by the application. We can try to create and assign some VRF according to the README file. So let's create VRF blue and go to config command, config mode, and sys VRF blue. Maybe I create one more VRF with error name. And now I can add this VRF to some interface. I can enable the interface and add VRF to it. And before I add correct VRF, I try to add the VRF that is not configured yet. So when I try to commit, the leafref validation rejected this, as this VRF is not present. So let's fix it. And now you can see that commit passed. And here are the commands sent by the adaptation layer, by the application to the device. You can see that both VRFs that I have created are created first, and then interface is configured. Now we can try to reassign interface and delete the old one. Yes. VRF. Let's try to first delete VRF. True. And when we try to commit, we again get error since VRF is assigned to the interface. So first we need to remove it from the interface. Port 0. Yes, and now we can commit, and as you can see here, VRF was first deleted from the interface, and only after that it was deleted from the system. Now we can create another VRF. And assign it. And again, commands were sorted in correct order, and device commands were issued and sent to the device. So this was short presentation of the ConfD application. In ConfD installation, you have this application present, so you can try it yourself. So to summarize, we have shown that transactionality is important, that it simplifies automation and programmability. The possible issues must be considered and avoided as much as possible. It's possible to use management system like ConfD to make non-transactional device transactional with full support of NetConf interface and YANG data models. NetConf support provides standard configuration and management interface, and key ConfD features for adaptation are validation and CDB subscriptions. These are the most common tasks that you need to implement when making transactionality layer. Such device can be easily plugged into NSO ecosystem, and it can then support network-wide transaction. Thanks to NetConf, there is no need to program adaptation layer or some special network element driver, net. And net can be auto-generated from device young data model with NSO command line script or with net builder. At the end, I can provide also some references to resources. On the TLF side, there is a resource page with other detailed training videos, and you can find a detailed video about CDB subscribers there, which can be useful when you are making adaptation, transactionality adaptation layer. ConfD itself is available. It has two editions. ConfD Basic is available for free with full support of NetConf, and it has also non-production CLI interface, which can be used for development and troubleshooting. ConfD Premium also features other interfaces like RESTconf, production CLI, and so on. ConfD Basic has community support on the Tail forum, and ConfD Premium has commercial support. Regarding NSO, it can be downloaded and tested for free in non-production environment. And so this is the last slide of the presentation. So I hope you have found it useful and learned something about how to add transactional layer to the application and what are the common transactionality issues. This presentation should be also available as PDF for download.
Thank you, Michal. I have a question on the demo. Is it available in ConfD Basic? I haven't checked.
I haven't checked as well, but I think it should be available as it works with NetConf interface, which is supported by ConfD Basic.
Okay. All right. So I have a second question here. I don't know if you can access. Can you open the Q&A?
Let me try to open it to find out.
Oh, okay. Thank you. Nabil said that it is available, so he checked. Thank you.
Okay.
Yeah. Can you read that question?
For some reason, I cannot switch to panel. Yeah, because I'm sharing. So I need to stop sharing my screen.
That's fine.
So I'll do this.
We have some time now for questions. So if anyone has any more questions, please type them here in the Q&A.
Large it.
Yeah, I'm not sure about the question clarity.
There is a question about third engine network transaction platform. It really depends what's meant by this. If it's some platform that it's transactional, one can, of course, make ConfD application. For example, if you have transactional platform that doesn't support NetConf, you can also write adaptation layer over this platform, which would be relatively simple as the transaction is already supported. And you can add NetConf support to this platform if this is the case for the question.
Okay, so there is an explanation here. Oh, there's another question probably. Regarding the dependency rules, are they represented in the Yang models? Should the dependencies rules described in the ConfD be a mirror to the ones that the network device has?
Yes, I think that this is, the dependency rules can be represented in the Yang data model with references. And in general, yes, they should be, they should reflect the device, but one has to consider if these dependency rules doesn't make transactionality issue that we have been talking about. For example, you need to be sure that you always configure dependent elements within one transaction, and that device can handle this in a correct way, or adaptation layer over device handles it. That means that when you add something that depends and it has dependency on something else, you must to have both elements, and also device must accept both elements within this transaction, or within this ConfD transaction. So the transactionality layer or device itself must handle this. And if these rules are problematic, they probably shouldn't be exported in the Yang data model, since it may lead to out of sync, and they should be handled by adaptation layer itself if possible.
Yes. So just to add to that, Yang and NetConf combination is the API to your device, the interface. It's also called the contract. What the automation tools and service orchestrator, network orchestrator tools see is Yang. So if you describe that dependency, which we call also semantic constraints in Yang, then that simplifies a lot of things, right? And that's part of the validation phase when orchestrator is validating the data before they even commit it to the device. So the more you can describe in Yang, the better. And that way you also reduce potential failures on the device once the data is considered valid by automation tools. There's another question here concerning, not probably question, but concerning transactionality. It's important thing that all vendors should support, but it's not the case. Yeah. The big problem is you don't know what's your vendor implementation limitations. So you start testing, then you face some issues. Yes, like there's an example here given for some issues with NetConf for a Huawei device. So yeah, there are. So that's the. Yeah, would you like to answer that, Michal, or comments on that?
Which question?
So there are, yeah, transactionality is something that should be supported properly by all devices that support NetConf.
Yes.
But in the field, there are still some equipment, some network element that still get it wrong. So that can actually break network-wide transaction support, of course, right?
Yes. And this should be handled by the adaptation layer if possible. Sometimes it's not possible, but in many cases, adaptation layer is possible to implement, and this usually fixes this.
Right. Can you read the second question from the bottom?
Question: when a rollback is not spot, is not spot, and the application logic returns an error. I'm not sure if I understand fully the questions. Is it the case when rollback on device is not spot, or is it the rollback of the ConfD? So in case if ConfD and ConfD adaptation layer does some configuration on the device, but the device itself performs rollback for some case, then yes, this rollback is not spot and you get the out of sync scenario. And now it depends on the adaptation layer. If it's sophisticated enough that can find out that there is an out of sync, and most probably in this case only alarm can be raised. So that's my understanding of the question.
Yeah. Okay. With regards to the difference between commit and confirmed commit.
Yeah. Okay. So commit. If NetConf device supports commit, then everything is committed in one transaction, which is okay. But if something goes wrong, then you just, yes, you have to roll back. You have to roll back the configuration. So you just send reverse configuration or call rollback. But in case you have support for confirm commit, you can just send commit or send configuration to the device and ask for confirm commit. And when you send this configuration to all other devices and you know that everything is okay, you just send confirm and configuration is applied. So you don't have to handle rollback on those devices if something goes wrong, because you just send abort commit and that's all.
Yeah, so basically this capability of ConfD can also be described as a two-phase commit, and it helps in implementing network-wide transactions. So in the ideal scenario, all devices in the network would be supporting confirmed commit, And it's a way for the orchestrator to orchestrate the change across all these networks, at the same time, so that if one of them fails in any of the phases of the transaction, nothing gets, so the devices would automatically roll back whatever they applied. It doesn't require the orchestrator to do that manually. So it's really cool feature. Just imagine it as a network-wide transaction, abstracting all the devices as a single device.
And for NSO, not all devices may support confirm commit, some may not.
Right.
But if they support confirm commit, the transaction and also handling of possible errors is very performant. And NSO doesn't have to spend time by inventing rollback and invoking a rollback and making sure that everything was rollbacked correctly. It just says abort and that's all.
Yes, thanks. Yeah, and not all the devices have to support. I mean, the devices that do support it, they provide that robustness and provide less headache for correcting errors.
And this is also the reason why to use some existing management agent like ConfD that adds this support and not to invent some proprietary transactional protocol and transactional implementation.
Right. Thank you. So yeah, we're reaching the end now. I'll make the recording available. When I get it, you'll receive that information by email. And with that, I'd like to thank you all for attending today. Thank you for the great questions. Thanks, Michal, for the presentation.
Okay, thank you all.
And thanks to all the panelists. So have a good day, everyone. Take care.